Good afternoon. So let us we continue our story about second quantization. But let me ask if there is anything in particular you would still like to see before I make a summary of what we have said. Okay, I start with the summary. If anything emerges, please stop. Okay, so the subject has to do with many identical particles, which will be of two classes, fermions or bosons. Fermions are those particles that have a half-integer spin. Bosons are those particles that have an integer spin, either 0 or any other integer. And we said that physics imposes, by some fundamental principles, different properties to the wave functions of those systems. Okay, different symmetry properties under permutation of the labels. Okay, so a simple, straightforward product of several functions is not, in general, good, especially for fermions. Okay. So we said that given a single particle Hilbert space, okay, with some basis which I call alpha, then we construct Hilbert space of several particles, okay, Hn, but rather than considering as good wave function simply the product, we have to consider, generally speaking, wave function of this form, sum over all possible permutations of, well, for bosons there is nothing to worry. For fermions there is a -1, so to combine them together I write it as C to the P, and then I have the permutation, okay, applied to a product state, alpha 1, alpha 2, alpha n, okay, where this is in Hilbert space 1, Hilbert space 2, Hilbert space n, okay, and we said that there is also 1 over n factorial in front in such a way that the fermionic case at least is certainly normalized, okay? So all those objects, we call it alpha 1, alpha n, okay? So these are correctly symmetrized states. As you see, what appears here is really the permutation applied to a product state, which we define to be the product state with alpha p1 for particle 1, alpha p2 for particle 2, and alpha pn for particle n, okay? So this is the exact meaning of this object. And the permutation, once again, is simply a reshuffling of the indices. So for instance, it associates to indices 1n a new reshuffled set with p1, p2, Pn, okay? So that's my notation. Pn means whatever is in position n after permutation, and so on, okay? Good. So this is the story of what are the good basis states. I'm not saying that these are ground state or excited states of any particular Hamiltonian, but these are the beginning of any description. So the basis state you have to take. Never consider only a product, because that would be not acceptable at all. Okay. Then we said that essentially the whole information that you need to take care is what labels are there and what are not there. Okay? So when you form a state, you have to tell me which alpha 1, alpha 2, and alpha n you involve in the state. It's not essential to tell me if alpha 1 goes to particle 1 or to particle 3, because in the end, everybody gets alpha 1 in turn, okay, with this sum over all permutation. I remind you, this is a horrible object, okay? So it's n factorial terms, so very, very many terms, which indeed you hope not to have to deal each, singularly. You hope to do things in some smart way. Otherwise, it would be killed by the factorial simply. Okay, so we said in second quantization, we introduce the following trick. We say, okay, let me just invent a state, a reference state, which I call the vacuum. And then, I invent an operator that sends the vacuum into this states alpha, whatever the basis of my Hilbert space was. Okay, this is an orthonormal basis that I can select the way I want. Okay, well, for every choice of those bases, I can define an operator A dagger alpha. Okay, so this is an infinite number, an infinite family of A daggers, not a single one like in the harmonic oscillator problem we did. Okay, for every alpha, an A dagger, but there are infinite of them. Okay, that's fine. That's the first step. But then we said even more. We said A dagger alpha is really the object that allows you to go from a state, say with, for instance, n minus 1 particles like this, okay? If I create A dagger alpha 1 on this, automatically I get alpha 1, alpha 2, alpha n, okay? So in some sense is an object that not only creates a label alpha from the vacuum, but it creates the label I associate to it on any state of n minus 1 particles, providing me a state with n particles now correctly symmetrized. Okay, so it does two jobs in one time: creates a label and automatically symmetrizes it. Okay, so in some sense, it's a bookkeeping device. I mean, it's something that simply tells from this state you get this when you create this. Okay, and this, each one of those things is a horrible object. So this is a sum over permutation of those labels. This is a sum over permutation of those labels. Okay, but this is a formal object. Okay, that I define in this way. So it's able to create as a single particle state, and even more, the n particle state, starting from n minus 1 particle state. Okay? Then we discussed that, well, essentially this implies that I can create all the labels one by one. Okay? So I can write also this thing in the following way, by induction. Okay? So starting from the vacuum, I create particle n, alpha n minus 1, and so on until the first one. Okay? And now you say, okay, well, what do I have gained? Well,
please.
Yeah.
Can we apply the separator to a gate which contains alpha 1?
To?
A state which contains alpha 1, the first one. Yes.
This one? Yes, you can, but you have to be careful. I mean, for boson, there is no problem. There is always the possibility of having in this object two indices that are the same. I mean, if alpha 2 is equal to alpha 1, doesn't really matter. I'm simply saying these are n minus 1 objects, okay? I'm not saying alpha 2 is different from alpha 1. It could be equal, okay? So suppose it is equal. So this is equal to alpha 1. Well, then this is alpha 1, alpha 1. Nothing really wrong. And this is alpha 1, alpha 1. Nothing wrong, except that if these are fermions, Pauli principle immediately tells you that this object is 0. Okay? So this is 0 for fermions. You can do it, but for bosons, fine, because you know that this thing is just totally symmetric, who cares? But since for fermions this is totally antisymmetric, it means that every transposition of two things brings a minus sign. But when you transpose something where two labels are the same, from one end you should get a minus sign. From the other hand, you get no difference, right? Because these are the same label. You can transpose it freely. It doesn't change nothing. Okay? So this fact immediately tells you that this object should be 0 if you are dealing with fermions. Okay? seen in first quantization, this later determinant associated to this thing would have two equal rows or columns. I forgot how. Okay.
Okay, you said that from this object, if we apply this object to the vacuum, we create some state.
Yeah.
Okay. If we start from the fact that the vacuum doesn't contain particles.
Right.
Okay, how this object applying to the vacuum creates some states.
I do not. I'm not sure I understood your question. What is the question again?
The vacuum
Yeah.
doesn't contain particles.
Right.
Okay, if we apply
Yeah.
a dagger
Uh-huh.
from the vacuum, we create particles.
Uh-huh.
So how is it possible since we start from a state which doesn't contain particles?
You mean how is possible that you have this thing, that a dagger alpha vacuum is a state with a particle in alpha? But this is the whole definition. It's a definition, okay?
Okay, I cannot understand.
I cannot explain to you the act of creation because it's one of the biggest mysteries of all the world, okay? This is a formal thing, okay? It means you have a Hilbert space, I have another Hilbert space, which it is just a single object, the vacuum, okay? There is an operator that acts on this and brings to the other, to the Hilbert space of the thing, okay? And it does so in the way I want, okay? It's my choice in some sense, okay? So you shouldn't investigate too much to the mystery of creation. There is nothing I'm creating. I'm defining, okay?
So it seems like vacuum contains some particles.
No, vacuum contains nothing. It's a single object, dull thing, which I write like this, okay? There is nothing there.
Okay.
What is physically? I mean, the moment before the Big Bang, what was it? I don't know. I have no idea, okay? So this is some arbitrary state which describes not a particle, but I can act on it, okay, formally, and create a particle, okay? Don't ask too much, because otherwise we go towards philosophy. We are not doing philosophy.
Vacuum doesn't contain particles. Why the vacuum image? Sir?
If the vacuum doesn't contain any particle, why?
Vacuum image. Since from okay, for example, if you take the image of an harmonic oscillator, okay, En equal h bar n plus 1/2. And the h bar, 1/2 h bar is the vacuum image.
Okay, let me, okay, what he's asking is, sometimes this vacuum is not really so vacuum, okay? This is a reasonable thing. In the harmonic oscillator example, okay, the vacuum was a well-defined state, okay? It was a Gaussian, in fact. He is right in this, okay? So in some sense, this is not nothing, okay? It's something you can think, you can draw even. So, I mean, however, the parallel here is slightly different. I mean, in some sense, in the harmonic oscillator, there's only one particle, which is always there. You do not create that particle. The particle is there from, I mean, all time. You create excitations, okay? So the excitation could be nothing, so the Gaussian, the ground state, or one excitation means you create an excitation above that Gaussian, okay? So in some sense, what I'm describing here as particles in the harmonic oscillator examples are not the particle, which is only one, but the excitations, okay, of that system. I don't know if I'm clear. So in the harmonic oscillator, I have one particle forever, okay? All the spectrum is relative to one particle. I do have the Gaussian, which is pictorially depicted as my reference state. And then I have the first excited state, okay, which has a node, which is A dagger 0. Okay, when I say there is an A dagger, I create a particle. It's not a particle in the usual sense. There is only one particle which is vibrating, but it's an excitation. So I'm create excitation, okay? Then I do the second excited state, okay? I have another excitation. So A dagger, 0. I have two excitations, okay? In some sense, the excitations here play the role that here play the actual particles, okay? I don't know if this is clear. So bosonic systems have this quite often. For instance, the photons. What are the photons? They are excitations of the electromagnetic field. You can have no excitation, so the field is just in its ground configuration, or you can create one and you see a photon. You create two and you see two photons, okay? So these are more similar to this picture, okay? What is the particle? No problem. I mean, in the harmonic oscillator, there is only one particle which is vibrating. In the electromagnetic field is a field, so you shouldn't describe it as, you shouldn't see it as a particle in some sense. But the excitations above a certain reference state, you can view them as particles, okay? So hope I'm not confusing you too much, but certain times you discuss of excitations as if they are particles. In other cases, there might be particles in a certain number and particles created or destroyed. So the two things can be treated in a very similar way. In fact, the formulas for bosons is essentially identical to the algebra we have done here, except that now we have more than one label, okay? But everything is exactly identical. But don't be misled by the fact that the vacuum, in the case of the harmonic oscillator, was a particular state. Because in some sense, in that case, it's not that I'm creating particles, I'm creating excitations. So there is a reference state, and there is then excitation created over this reference state. In the particle case, you should imagine that this vacuum is something which you wouldn't need to plot. It's something where you create directly the particles, okay? So in some sense, there is no need to write the wave function of this, okay? There is no such a thing. You don't care. It's something that stays there just because in this way you can apply to it something, a dagger, okay? The whole, how should I say, the whole purpose of this state is that you can write this equation. That's it. That's the only meaning, reasonable meaning that you should give to that expression, okay? So you shouldn't think of this as some state with the Gaussian type of thing like there, okay? This is a different thing. Hopefully.
This is for all quantum systems.
For all?
Quantum systems, because we know from quantum theory that for each quantum number is associated. We have to have the vacuum energy. So we cannot.
It's enough to have one vacuum. One vacuum is enough. It serves all the things, okay? So with one vacuum applying, you create any label. There's no need to have several vacuums for every label, okay? It's one is enough.
So each quantum system has one
Yeah.
one the corresponding vacuum energy, which seems to be as a state. Since we have the energy of the vacuum, but not vacuum, we have to consider this vacuum as a state.
Look, I have two brief comments. I think we should also truncate this because the two brief comments are this. There are several branches of quantum physics. There is also quantum field theory. So if you talk to a quantum field theorist, okay, he would have much to say about vacuum and fluctuations of vacuum and Casimir effect, for instance, okay? So the vacuum of a field like the electromagnetic field is not that vacuum in some sense. There is a field between the plates of a condensator, okay? If you just put two metal things, okay, the photons of the field in that region have to be quantized in a particular way. For instance, they must obey some boundary condition. And this automatically has some zero-point energy, okay? And this zero-point energy depends on the distance between the two plates of the condensate. So in field theory, there is a lot that can be said about vacuum and vacuum fluctuation. But in non-relativistic many particle theory, you shouldn't smash your head too much on this big wall of in between field theory and philosophy, okay? It is a simple formal object. One object such that you, I mean, if you want to build a wall, you must have some floor, okay? And then you start having the thing, okay? So if I want to build this thing from something, I might need a floor. The floor is the vacuum, okay? So I build on this a particle, second particle, third particle, and here comes the wall, okay? That's it. No philosophy, no deep things. There is nothing really behind. Okay? In some sense, the harmonic oscillator that you already know is more similar to the quantum field theory point of view than to the many non-relativistic particles point of view. Okay? Because there the vacuum is something. Okay? It has a zero-point energy, and okay. But that's it. Okay? If you have in mind that this is well understood to you, you know how to draw this, and it's more in the spirit of field theory thing, okay? So creating excitations on the back. And this is just a floor to build a wall, that's it. The rest is too much beyond what I know, by the way, okay? So I shouldn't just... All right, other questions? You can, I mean, we are free of, we can discuss even for half an hour, it's all right, but I wouldn't be able to add much more physical understanding in some sense, except for referring to your colleagues of quantum field theory, or to ask for details of the, what is a vacuum there, how comes that vacuum has fluctuations, and okay? So this is another story. You shouldn't be worried about any subtle thing here. It's just a reference dull object, okay, which is there such that you apply some A dagger, and there comes a state, okay? So in some sense, this thing alone doesn't know how to create a state, okay? It needs some building ground, and the building ground is the vacuum. Once you have the building ground, then you create A dagger alpha, and there comes a single particle state, and then one after the other, you create your n particle state. Okay?
So this state is contained in the A dagger or in the vacuum?
Which state?
That state, the state that...
When you build a wall, okay, the whole construction is contained in a single brick or in the floor. I mean, it's the result of a floor and the bricks, okay? So you need the floor, okay, and the bricks to build the whole wall, okay? So the state is made of creation of the bricks on the floor, okay? Where is it? It's there or there, in both, okay? Nothing. You shouldn't think too much. That's my only urge. Thinking too much sometimes brings to the I mean, how should I say, to the verge of a very strange area, which is unclear between philosophy, physics, mathematics, and cosmology, and then things become very blurred, and you don't really know who you are, what are you doing, okay? So just think very practically, okay? This is a device, something that allows you to express every state by a single application of this, and even more nicely, you are allowed to think of this object as applying n of those guys to a floor, the zero, okay? Now, this automatically implies the correct symmetry because I impose the fundamental rules. So for instance, for fermions, two A daggers, A dagger alpha prime, anti-commute, Okay, this is the anti-commutator. It means if you exchange it, you get a minus sign. For bosons, it would be the commutator. Okay. Then we started discussing several properties. In particular, we introduced not only the A dagger but also the A. Obviously, the A does the opposite. It destroys. Okay. The A destroys things. So it means that if I have, for instance, some state with A dagger alpha, okay, and then other A daggers here, alpha 2, okay, then the destruction of alpha simply removes the alpha that you have created, okay? So it's like undoing a construction, okay? You take off the brick, okay? If it is the last brick, you just take it off without paying any minus signs for fermions. If it is a brick inside, okay, so we discussed that if I have A dagger alpha 1, A dagger alpha 2, A dagger alpha I, A dagger alpha n, okay? And we discussed that if I want to destroy the brick here, alpha I, then before doing that, before removing the brick, I have to bring the, how should I say, the hammer and thing, the destruction object there, which requires anti-commuting this object with I minus 1 A daggers, okay? This brings a sign minus 1 to the I minus 1, okay? So the object would be now alpha 1, alpha 2, a hole there. There's nothing. There's no I dagger alpha high. And, well, but you shouldn't think that I have to put a hole. It's just to tell you that there is no such a thing, okay? Then there is I dagger, the following one, alpha I plus 1, and then there is the last one, okay? Is this clear? Okay? So the A removes a brick. If it is in first position, it removes it without any problem. If it is somewhere in the internal thing, for fermions, you have to be careful. You remove the brick, but you pay some minus sign, possibly. Okay? When you, however, create again, for instance, if you do this thing, you remove and then you create, okay? Then the thing is pretty simple. So what you do is, again, you can put the label alpha I that you just removed back in, okay? However, to put it exactly in the position where it was, you have to anti-commute this object with I minus 1 objects that are before the place you want, okay? So you pay another minus 1 to the I minus 1, okay? So when I do this, when I bring this there, I get another factor like that, which makes a total plus 1, okay? So the result is just equal to A dagger alpha 1, A dagger alpha I, A dagger alpha n, vacuum, okay? So in some sense, this is exactly the way it is saying that this operator here, okay, simply if alpha is a label that is included in this list somewhere, is simply counting now that there is one label. You see that this object here is an eigenstate of this operator with eigenvalue 1, okay? So we also define this object to be the number operator, okay? The A dagger alpha, A alpha with the same label counts. If there is the label, you get 1, as in this case. If alpha is not there, so if this was some alpha which is not contained in this list, then you would bring the destruction operator all the way to here. And here comes the second property of this dull object, which is the vacuum, is that if you try to destroy something on the vacuum, okay, it's like trying to take off a brick when there is no brick, it's only the floor, then you get 0. Okay? 0, not the vacuum. Okay? So these are the two properties of this mysterious object that you have to have clear in mind, okay, as practical devices, okay? So don't think too much of really how do I really destroy the vacuum and what is after the destruction of the vacuum, because again, it looks like a very profound question, but in some sense has nothing to do with the theory we're doing, okay? Which is not the theory of the universe, but the theory of a system of n identical non-relativistic particles, all right? What is the question again?
If we apply a dagger to the first excited state.
First of all, don't talk about first excited state. I haven't talked here about excited states. Those states are not excited states. I don't know the Hamiltonian yet, okay? Those are states, not excited states.
Okay, the first states that we create, we can create from vacuum the first state.
Yeah.
Okay, and
And then I can create another. So for instance, if I created the first particle, alpha 2, then I can create another one in alpha 1. And alpha 1 might be identical to alpha 2 if I have boson systems, or different. If I
So we are not creating state but operator.
No, I'm creating states. The operators are there once and for all. For every alpha, you define an operator, okay? I'm creating now the state. This is the state alpha 1, alpha 2, okay?
What if we apply a dagger to the state?
I am applied a dagger to the state. The state is this, okay?
The last one. This one, alpha 1, alpha 2.
I'm not sure I understand what you ask.
Yes. Okay,
Do you want another a dagger? You want a third a dagger? I can put whatever number of a dagger. Tell me a number and I put it for you. Tell me the label. Which label you like? 13. Alpha 13. Okay? Here it is. I do not catch what is the question.
So there is no coefficient in front of.
No, no. That is my this is definition. Definition. Okay? Definition. You know, I mean, when you have an axiomatic theory, you have some postulates and some definitions. You do not ask, why do you postulate this? This is a postulate, and go on, okay? So this is it. The only thing I must show to you is that with this kind of tools, you calculate exactly the right things, okay? So if I am able to show to you that those states are perfectly well defined, okay? And you can calculate any average you want, then with this trick here, then this is automatically good guys, okay? They serve the purpose of calculating things, all right? But in order to do that, you have to admit that I start from something, okay? I must give you some objects to work with, okay? And the objects have these basic properties. If with these basic properties I'm able to show that you can do whatever you used to do in first quantization with all the sum over permutation and things, which would be a horrible mess, then this is a good thing, okay? It's an instrument of calculus which makes life simpler, okay? You don't ask why, you just are grateful for the fact that this is simpler, okay? So, provided I'll show you that this is simpler. Okay? So I don't know if I clarified with this. I mean, there are states, and you can keep creating labels on those states with extra a dagger. All right? Maybe. Okay. Good. So what I was saying is that if alpha is not included in the list alpha 1, alpha n, then when you try to destroy alpha, you get just 0, which means that n alpha, this object, is equal to just 0. Okay? So in some sense, this operator counts. If alpha appears there, you get 1. if alpha does not appear, you get 0. Okay? It's a number operator, it's called. Okay? And I must insist on the fact that for bosons, more than one time a certain label might be present. Okay? We haven't done this. We'll do it tomorrow in more detail. So all the modifications you need to do for bosons, we will try to catch them tomorrow. But for bosons, certainly there can be more than one time the label. Even all labels might be identical, for instance. Okay? I dagger alpha, I dagger alpha, I dagger alpha, I dagger alpha. Okay? In that case, n alpha would count how many you have. Pretty much the same thing that you do in the harmonic oscillator. If you remember, if I have a dagger A into a state with a dagger, a dagger, a dagger n times, okay, then this object would be simply equal to n times the same state. Okay? You remember this? Harmonic oscillator. Okay? The same thing. It counts the number of excitations that you have created on the vacuum. So this is an operator here, and this is just a number, n. Okay? For fermions, this could be just 0 or 1, because there is no possibility that you have more than one time a label applied. Okay? Is this clear? Okay. So these are the basic objects, the A daggers, the number operator. We discussed that not only you have this, but you also have the other rules, for instance, for the A, similar. And for the bosons would be this, A dagger alpha prime. And you also have a third, more interesting one, that if you have an A with an A dagger, then the anti-commutator gives you a delta, a Kronecker delta, alpha prime. Okay, we verified last time the fact that the application of A dagger or A dagger A in the opposite order, when the label is different, has an extra 1. Okay, just try to look at the algebra we did last time. For the bosons, it would be this. Okay, pretty much as for the harmonic oscillator example, except that in that case there was only one alpha, okay? No label at all, so we had just one, no delta, okay? But in general, if you have more than one label, you have a delta, Kronecker delta, okay? Not Dirac delta, Kronecker delta. This commutation relationship are the whole you need, okay? The rules of the game, okay? So this is a game. And what you see here are the rules of the game. With these rules, I anticipate to you, you can play the game of calculating any objects that in first quantization would appear a horrible mess of sum of permutations and things like this, okay? Now, let me proceed a little bit, because after all, what I've done is to play a game of writing a state that looks complicated into a form that looks slightly simpler, but this looks like a trivial exercise. What do I do? What do I do if I write a state in a simpler form when I do not calculate anything with the state? Okay, really looks like an aesthetic type of thing. Yeah.
I don't see the difference between the four commutations.
The what?
The four commutations.
Which one? Which four?
The first, yes.
This
Yeah,
and this?
Yes.
First of all, these are anti-commutators. They apply to fermions. These are commutators. They apply to bosons. Okay, so the two lines are fermions, bosons. Second, this is A dagger. You see there is always a 0. This is, on the contrary, A dagger. There is a delta. So sometimes there is a 1. Okay? That's it. That's the only thing I'm saying. Okay. So now comes the first really crucial thing, and it's the following. Suppose that I want to calculate some expectation value of an operator in between two states, okay? Here comes the usefulness of the game I have introduced. Okay, let's see. So, oops, I have made this thing very ugly now. Okay, so I propose the following thing. Suppose that I ask you to calculate the expectation value of a certain operator. Let me call it U, okay? This operator is a one-body operator. What is a one-body operator? Let me explain to you. You remember probably when we discussed helium, okay? We said the Hamiltonian of helium is sum over I is the several electrons, in our case only 2 really, but in general you can think of having n electrons. Then there is pi square over twice the mass minus z e square over ri, okay? So you see this object looks like sum over several, at this level, independent variables, the p and the r of each single electron, without any interaction between the particles, okay? So whenever an operator looks like this, so sum over all i's of operators that depend only on the I quantum number, on the I variables, r and p, I, then this is called one body, okay? In some sense, it tells the obvious things. It's something that looks at the particle, decides something, and sums over all of them, okay, independently. Okay?
We can reduce to a one-body problem, right?
Yes, okay? Yeah, in essence, if you have only this, life is simple. And I will show it to you in a second why it's simple. Because the whole thing is, I mean, we'll see in a second, okay? So, in general, even if you have n particles, this would be a one-body operator. On the contrary, for instance, Coulomb interaction looks like this. Sum over I different from j, E square Ri minus Rj. So you see now I have to look at each pair of particles, okay, and involve the variable of each pair and calculate the resulting effect of the operator, okay? This is an operator that is diagonal in space representation, obviously, but you can think of other operators that are necessarily not diagonal there, okay? In any case, this object is a two-body operator, okay? Usually you do not involve more than just two-body operators. I mean, in certain phenomenological theories, you might be willing to introduce even three-body potentials or four-body potentials. In nuclear physics, I think that they tend to like complicated phenomenological objects, but even sometimes in certain condensed matter problem, but usually are phenomenological approaches where they try to mimic. Okay, so the basic thing we will need, I mean, we would be very, very happy if we know how to deal with a two-body operator like the Coulomb interaction. This would be indeed, most of condensed matter would be simple if I were to know to treat a problem like this, okay?
What's H? Is it one body or two body?
Which one?
H at the big H, the sum of
The H has one body terms and two body terms, okay? So H is neither one body nor two body, okay? So it's the sum of a one body term and two body term, okay? So when I say take a one body operator, I mean take, for instance, this piece only, okay? This object in first quantization looks always something like sum over I from 1 to n, a u that depends on the variable I alone, okay? That's it. And second, a two-body operator would be an operator that has the following look. Okay, now, I want to, in principle, do the following. I have this operator, and I want to calculate the expectation value of a state alpha 1, alpha n, and on the left, some other state, alpha 1 prime, alpha n prime. Okay? So this is, for instance, if you remember when we did the hydrogen, the helium, that's exactly what we calculated. We tried to calculate the energy of a Slater determinant where we put the 2 electrons, for instance, in the 1s orbital. And we asked, what is the average energy? The average energy was made of 2 pieces, the contribution from this and the contribution from the Coulomb interaction, and we calculated both, right? If you remember, we essentially wrote this thing, and we calculated it. But at that level, it was only 2 terms appearing. Actually, in fact, 1, because the function was anti-symmetric in the spin, was a singlet, and just a product of 2 identical orbitals, okay? So there was absolutely no complication at all. But now, in principle, you see what you have. You have a sum over the permutations there. Okay? So this would be 1 over square root of n factorial sum over permutations of, for instance, for fermions, minus 1 to the p, alpha 1, alpha n. A similar thing here. Okay? So 1 over n factorial sum over p prime, minus 1 to the p prime, and alpha 1 prime, alpha n prime, p prime, acting on the left. Okay? And in the middle, a sum like that. Okay? So you see n factorial, and n terms. Okay? So if I start having, say, 7 particles, or even less than 7, let's do 3. Okay? That would be 6 term here, 3 factorial term. 6 here, and 3 in the middle. Okay? 6 times 6 is 36, times 3 is 100 and something. Okay? So you realize immediately that the number of terms and the sums appearing are quite large. Obviously, I'm not saying that if you do like this, you wouldn't notice immediately that many of these terms are reduced to each other. Okay? So I do not pretend that you believe that you sit down and you calculate 100 and whatever, 108 integrals. I know that you will notice that there are essentially very few integrals that you need to calculate. All the terms are related by permutation. Okay. But that's exactly the point. Since the state is just a very trivial sum over permutation, there is really no need of carrying all this information. It's enough to know which labels are there. That's the point. And that's what second quantization does very effectively. Okay? It essentially eliminates for you the burden of knowing that the state is really sum over permutation. Who cares? Tell me just what the alphas are. Okay? That's the point. Now, let's see how it works more in detail. Yeah.
We saw that if we want to eliminate one of the A daggers, if the A dagger is in the middle, we gain -1.
To the number of A daggers before.
Yes. So is it also necessary to know the order of the initial state?
Yes. That's a very interesting question. The question is the order in which the particles, the labels appear here, or if you want equivalently, in which the operators appear there, is important. Yes, it is. Okay? It's not important in the sense that, they are all related. Different orders are related by certain change of signs. Okay? But indeed, sometimes this implies a crucial minus sign, which could change some of the physics. We will see an example later on. Okay? So the order is in some sense a convention. Okay, you decide once and for all if you want to put first, for instance, suppose that these were the labels of the hydrogen atom. You can decide that you order the states in the, say, from S, then SP, then SPD, and so on, in the order in which they appear, okay? Because it's a convention, okay? There is an ordering convention, okay? But once you choose a convention, it's important that then you respect the rules, okay? So when you change two things, you pay a minus sign. If you have to go to a place, you count the number of signs, okay? So it's irrelevant what is the initial convention, but once you fix, keep it, because otherwise the number of minus signs that you have in your final result is completely wrong, okay? So half of the time will be right and half of the time will be wrong, okay? Because it's just, okay. So, very interesting thing. The ordering is a convention, but is important to keep and have it. Okay, so I will do this proof. I want to prove the following thing. I essentially want to prove that that operator in second quantization looks as follows. It looks as a sum over alpha and beta of an operator A dagger alpha A beta, okay? So something that is similar to the number operator, but this time with in general two different labels. And here I have the matrix element of this object, U, each one, I mean, just take one between alpha and beta, okay? So a one-body operator in second quantization will look as a sum of objects like A dagger A, okay? A single pair, one A dagger and one A. However, all labels are in general involved, and the weight that you have to put in front is the matrix element of the operator that you are dealing with, okay? So for instance, if it was this, then this object here would be the integral over the R of P squared over 2M minus Z E squared over R times the wave function of label beta, R, the wave function of label alpha, star. Okay? Is this clear? Now, you just calculate once and for all the integrals that you need here, whatever they will be the important one, okay? And at that point, the operator is just that. Okay? This is what I have to show to you, okay? Don't take it as a, until now, I have just introduced the rule of the game, and I told you that the states can be written in this way, and there are some tricks about how to manipulate the states, but these are simple consequences. Now I would like to show the crucial thing, that in some sense, I can write also not only the states, but I can write the operators. For instance, the one-body operator would look like that. Then later on, I will show you how to write two-body operators. Okay? Rather than tackling the general problem like that directly, let me do it in two steps. So in the first step, I assume that the basis alpha, so assume alpha to be eigenstates of U. Okay? This is not of any UI. This is a particular choice, obviously. It's not the most general basis. Okay? So in the present case would be alpha should be hydrogenoid functions. Okay? So eigenstate of P squared over 2M minus Z E squared over R. Okay? For any other basis, I will do it in the second step. Okay? So let me just do the first step. Assume that alpha is eigenstate of UI, so in this case of this object, and see how it is that the operator is that. Well, in fact, for that choice, this way of writing is even simpler, because if these are eigenstates of U, okay, then this object here you immediately see is simply U beta times delta alpha beta. Okay? Is the eigenvalue over the state beta, or the state alpha is the same, times the delta alpha beta. And therefore, the double sum over alpha and beta, for that case, so again, alpha eigenstates of ui would be a single sum with the u alpha value, the eigenvalues, times a dagger alpha, a alpha. And what is a dagger alpha, a alpha? Is the number operator, okay? So in that case, the second quantization expression would be this, a very simple expression. Okay, let us see that this is indeed the case. Okay, there are obviously a few things to consider. First of all, this operator here in first quantization, I'm looking at the first quantization expression. Then I will look in the second quantization language and I will notice that they are exactly the same thing. So in first quantization, as I said, you have the state that you write like this, the other state that you write like this, and the operator that is in principle that. But if you notice, this is essentially 1 over n factorial. Then there is a double sum over permutation p and permutation p prime. Then there is a factor, it is in general z to the p, z to the p1, c or z, whatever. And then there is what? And then there is essentially the operator p prime. Then this operator here, which is the sum over all I of ui, the operator p on the right, and then I have alpha 1, alpha n, and here alpha whatever. You can decide the order. Let's put it, the 1, I put it immediately. So alpha 1 prime, alpha n prime. Okay? This is the object. Now, notice one thing. This operator is summed over all indices. So in some sense, a permutation does nothing to it, right? What I say is the following. P to the minus 1, sum over I, ui, p, should be just equal to the sum over I, ui. Okay? Doesn't matter if you permute, then you apply, and then you apply the permutation back. Okay? Because they are all summed, so who cares about what permutation you have done? Okay? So this is one obvious thing, which immediately tells you that you can add here a p to the minus 1. Okay? Okay? And after that, you notice that here I simply have the same operator. So this is identical, this object is identical to alpha prime n, alpha prime 1, the p prime that is there, times the p that is there, times p to the minus 1, the sum p, which is just sum over I, ui. Alpha 1, alpha n. Okay? This might seem like a trivial thing. So essentially I have brought the p from the right to across that. Okay? Which I can do because what is in between is you might say, why do you do that? Well, look, now I have the product of two permutations. Okay? Call this object p second. The product of two permutations is still a permutation, right? And the parity of that permutation is exactly the product of the two parities. So what you have here is also c to the power to the p2. Okay? So in some sense, I have a sum of 2p and p prime. But really this means summing over p second. Almost, except that these are n factorial term, so n factorial square term, while this is just n factorial term. So there is an extra factor, n factorial, which indeed cancels that n factorial there, okay? So the result is identical without n factorial to a single sum now over the permutation p second, the factor usual factor -1 or +1 to the p second order times now the following thing, okay? So the p second acting only on the left and not on the right, okay? Now, this is a bit better from the bookkeeping device. First of all, I have reduced already an n factorial number of terms, okay? By just using the properties of the operator inside being totally invariant under permutation. Okay, that's good. Let's proceed. Now, this object, obviously, let me write it explicitly. I should write it here, perhaps. So this is equal to the sum over all permutations. Rather than p second, let me just call it again p. The sum over all permutation p of c to the p. And then I have here the operator p acting on the state, which means what? It means alpha prime pn, alpha prime p1. Then I have in the middle the subject, sum over I ui. And then I have the usual alpha 1, alpha n. Okay? Good. So this is the step I have done. Now let me make some space here, because I still need to do some gymnastic. This is okay. This is okay. Good. This means a precise thing. This means Hilbert space 1, Hilbert space n. Okay? This again means Hilbert space 1. This means Hilbert space n. Okay? So each one cares about the particular, for instance, u1, okay, which is the operator that has to do with particle 1, takes care of this and that. Okay? u2 takes care of the second and the second. un of the last and the last. All right? So actually, the sum really means that I have to do a sum of, well, sum over all permutation is there. C to the p is there. But really, this object is, for instance, something like alpha. So for instance, the first one would be alpha prime p1, u1, alpha 1, and all the others without any u, okay? So alpha prime p2, alpha 2, alpha prime pn, alpha n. Is this clear? Okay, this is only the first piece, the u1. Then there would be a term with u2, where the first term is just without anything. The second would have the u2. Okay? And all the others, again, without any u. And then there is the third, the n, and so on. Okay? So if you allow me, this would be something like, is this clear? Okay? It's important that this step is clear. Because now I would write it in a slightly more condensed form. So plus all other ui terms. I would write it like this, if you allow me. It's a sum over all I from 1 to n, then a sum over the permutations, c to the p. Then I have, you see, I have always some alpha pi prime with ui and alpha I, and all the others, so all the other j different from I, are simply written like this. Okay? So all the j's that are different from the I have selected appear without the u. And the I1 has the u. Okay? And then I have to sum over all i's. Is this clear? Good. But now, remember, this alpha choice is a basis of eigenstate of ui. Okay? So this object here, how much it is u alpha I, sorry, times an entirely similar object like alpha prime pi alpha I. Okay? So it looks exactly like those, except for a prefactor u alpha I. Now, you see this prefactor u alpha I doesn't depend on p. So I can even take it here. Okay? So let me write it as u sum over I from 1 to n u alpha I. Okay? And then I have the sum over all permutation p, xi to the p. Okay? And then I have what? I have the product of the I term and all the j different from I. So products of all terms, right? So I have, once again, say alpha prime p1, alpha 1, alpha prime p2, alpha 2, until alpha prime pn, alpha n. Okay? Good. But what is this? Well, if I ask you to calculate this without the u, what you get is exactly that, obviously. You do the same algebra. So you know that this is nothing but the scalar product of this state with that state. Okay? So this object is also equal to sum over I from 1 to n u alpha I times alpha prime 1, alpha prime n, alpha 1, alpha n. Okay? This is the last step of this quite lengthy algebra. Okay? So again, not 108 integrals to calculate, but certainly a lot of gymnastic and a certain number of integrals that you must calculate. Okay? So if it was 3 particles, then you must calculate u of alpha 1, u of alpha 2, and u of alpha 3, the 3 that are there. Okay? 3 integrals you have to calculate, but not 108. Okay? That's the resulting first quantization. Now, second quantization. Okay? Let's see how to do this quite rapidly. I should use some space. Which space? Well, let me erase the first line and substitute with this. So for the choice I've made, this would be sum over alpha, u alpha, n alpha. Okay? So I now calculate the result. Okay, so this operator is like that. So I have sum over alpha, u alpha, n alpha. Then I have the state on the right that is essentially a dagger. Well, I don't even need to write it in second quantization. I could write it like that or simply like this. Alpha 1, alpha n. Okay? So to restate this in second quantization would be I dagger alpha 1, I dagger alpha n built on the ground, on the floor, on the vacuum. Okay? So on the left, I have alpha prime, alpha n prime. Okay? Again, a certain number of A daggers. Now, look at the actor in the game, n alpha. N alpha counts. Okay? So it looks, who is there? Okay? There is a sum over all alphas, but some of them, the ones that do not appear, count 0 because they produce an eigenstate of n alpha with eigenvalue 0. On the contrary, the alpha that appear, so alpha 1, alpha 2, alpha n, produce a 1. Okay? So the result of this immediately is sum over all alpha I, so sum over I from 1 to n, of u alpha I times 1 times the state itself. Okay? And then you have to take the scalar product with this guy. But this is a number, so let me put it here. Alpha 1 prime, alpha n prime. Okay? You see one line, and I got the same result. Now, what is the miracle? Nothing, really. These objects were constructed to simplify life. Okay? They are artificial objects. That's the reason why I do not, I invite you not to think too much about what it means, the vacuum. It's a formal thing, but it's a very, very useful formal object, which allow you the bookkeeping of the permutations very, very effectively. Okay? So in some sense, the only important thing in a state is which labels are there. So it's a counting problem. Okay? So if you are able to count how many times a certain label appears, if it is there or not, that's enough. And you see, in general, all the integrals that you need are just the integral related to the labels there. Now, if obviously these two elements are the same, okay, for every possible choice of alpha 1, alpha n, alpha prime n, it means that this is indeed the form of the operator, okay? I have verified that the matrix element on any pair of states coincide, and therefore this must be the way of writing the very same operator in second quantization. However, this is only step 1. I did all my verification in a very specific basis, okay? So I verified that this operator in first quantization is written in this form if alpha is the basis of eigenstates of U. Now, how do I write the most generic form of U whenever alpha is a generic base? Simple. I know how to change bases, okay? We said last time if I have a certain basis with creation operator A dagger alpha, and I have another basis with another set of creation operators, then I can change from one to the other. And therefore, that's the second step I'm going to do. I'm going to take this basis, which is very particular, and transform to an arbitrary basis, and there will come the general form of the operator. Okay? So this is the second step. Needs very little, but let me just redo it. So the second basis, how should I call it? Lambda, okay? So there is a basis lambda now, which is obviously a certain superposition of alpha states. So how do I write? Well, it's always the same thing, right? Sum over alpha, 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 the identity, times lambda. Okay? So this is simply some matrix, some unitary, in fact, matrix. These are two orthonormal bases, so some U alpha lambda object. I don't know how I called it last time. It doesn't matter, okay? So this means that A dagger lambda in this new basis should be equal to the sum over alpha of A dagger alpha times U alpha lambda. This is one formula, but you need, in fact, the opposite formula. You need to express the alpha, which is the good one that I have used until now, in terms of a generic lambda. What do? The opposite. So you say alpha should be equal to sum over lambda, 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 alpha, okay? So, yeah, so this implies that A dagger alpha is sum over lambda, A dagger lambda, times this object, which is nothing but the star of that, by the way, okay? So you can write it as U alpha lambda star. Okay. Once I have this, I can plug into, and I need also the one for the A alpha. A alpha is sum, just take the Hermitian conjugate, sum over lambda, A lambda, U without the star, alpha lambda. Okay? So I now plug into the formula there. So U in the good basis is sum over alpha. Oh, oops, I'm calling U too many things. Sorry. This matrix here, how should I call it? This change of basis matrix. I'm sorry, okay? This was not planned. Omega, you like omega. Okay, omega. Big omega. So the matrix that changes basis is, or I could call it S. S is a nice thing. S. Okay. Good. Okay. So this is U alpha, sum over alpha. Then I have N alpha, which means A dagger alpha, A alpha. Then I put these expressions there. Obviously, I have to use two different lambda when I sum. So this is sum over alpha, U alpha. There is a sum over lambda, a sum over lambda prime. And then I have here A dagger lambda. And then I have S star alpha lambda. And here A lambda prime and S alpha lambda prime. Okay? And then I rewrite this as sum over lambda and lambda prime of A dagger lambda, A lambda prime times a matrix element here that is sum over alpha of U alpha S star alpha lambda S alpha lambda prime. Okay? So let me conclude this thing with showing to you that this object here, this is what? This is a sum over alpha of, let's see, S is simply this object. So this would be, for instance, this would be the alpha lambda prime, okay, here. Here I would have the star of it, so the lambda alpha. And in the middle I have U alpha, which is alpha U alpha, okay? Now, you see immediately that this object here, in fact, you see that this is diagonal, okay? So this object here is really, I could introduce a sum over two different alpha and alpha prime, and for instance, write this as alpha prime, because this, after all, introduces a delta, okay? Once I write it like this, it's immediately obvious. This is an identity, and this is another identity. So this thing is simply equal to lambda U lambda prime, okay? So in this squeeze, this is nothing but the matrix element of U in the new basis now, lambda, okay? So this thing is simply equal to sum over lambda and lambda prime, matrix element of U and operators A dagger lambda, A dagger lambda prime, which is the form that I was proposing to you first, okay? So once again, in the specific case where these bases is eigenstates of U, the double sum simplifies and these objects become the number operator. But in more general terms, they would have A dagger A with different labels, okay? Good, this was quite long and tiring, okay, to show that, I mean, there was a sense in doing this, okay? It actually simplifies a lot when you have to calculate matrix elements. not so much the aesthetic, okay, of writing an object like a product of things rather than a sum and factorial. It's really a practical aspect, so calculating things in a much slimmer way. Now, to finish the story, I should really touch and explain the same thing for the two-body operators, okay? I don't want to make it, however, that long, because otherwise you would be killed, essentially. The story is almost identical, except that in the proof and in all the things, I have to be careful, because now the operator touches two objects at a time, I and J, not I, okay? But much of the story is identical. So the operator that I'm considering now, let me call it V, which in second quantization is sum over I, different from J, some V, R, I, and J, is certainly totally symmetric under permutation. So something like P minus 1 V P is essentially equal to V, because I'm summing over all possible pairs in all possible ways, and therefore it doesn't matter if you permute in any possible way. Okay? So you repeat exactly the same reasoning that we did for the one body, but keeping track of the fact that now the objects involve two things and not only one. Okay, so you have two objects that you take the sandwich of V and the other n minus 2 that go one with the other. Again, you start in two steps by assuming that the basis is eigenstates of V, and then you generalize in pretty much the same way as we did here, okay? So you repeat the same thing, the same steps, and if you do it, you discover the following thing. That oops, is this okay? Okay. If U sum over I, Ui, in first quantization is written in general, now I call alpha now a general basis, not as sum over alpha, alpha U beta, or should I perhaps use alpha prime rather than beta so that it's more consistent, A dagger alpha A alpha prime. Then for V, I have a more complicated expression, but not infinitely more complicated. There is, first of all, 4 operators, okay? So there is A dagger, A, okay? Not 2. It's 2-body operator, so 1-body operator, 1 A dagger, and 1 A. 2-body operator, 2 A daggers, 2 A. 3-body operator, 3 A dagger, and 3 A, okay? Let's be happy with this. So there is now rather than a sum over alpha and alpha prime, in general, you have to admit a sum over, say, alpha 1, alpha 2, okay? And then alpha 1 prime, alpha 2 prime, okay? So rather than having a single object and its prime, now I have well, I'm writing with a slightly different notation. I'm putting the prime now here and the thing there. Okay, so to have a similar notation, I should have that. Okay? And here I have a matrix element of this operator V, V, for instance, 1, 2, in between states alpha 1 and alpha 2, and going into states alpha 1 prime, alpha 2 prime, okay? And the factor 1/2 in front. Okay, so let me summarize. I have sum over alpha 1, alpha 2, alpha 1 prime, alpha 2 prime. Okay, so 4 labels. I have 4 operators with indices alpha 1, alpha 2, alpha 1 prime, alpha 2 prime. Notice, however, the order. As she was noticing, the order is not irrelevant for fermions. So it's important, for instance, that the alpha 1 prime I put it close to this guy here and not further away. In other words, if I exchange these two, which I can always do, I should be careful. For fermions, I would get a minus sign. Okay? In this way, there's no minus sign for, I mean, it's right like that. You might say, I mean, who cares about, I could change labels and I just, yes, I mean, it cares because you see, the labels, the way I have chosen the labels here, it's consistent with what I'm writing here, the matrix element, okay? Let me just finish this description. With the following clarification. The matrix element, in that case, was a simple object, right? So this one would be a single integral of u of r, for instance, between phi alpha of r and phi alpha prime of r star. Now I have a double integral, so this object is an integral over r1 and r2. And then I have v of r1, r2. Sorry, let me make more space. v r1, r2. For instance, e squared over r1 minus r2. Then I have phi alpha 1, r1, phi alpha 2, r2. Okay? And then I have, on the left here, the same r1 carries the label alpha 1. Okay? And r2 carries the label alpha 2 prime. Okay? So in some sense, there is a natural association. These two operators that are close by, in the way I write it, are really the ones, okay, whose labels are associated to the same particle, particle 1 in the matrix element. Okay? And similarly, alpha 2 and alpha 2 prime, which are further apart here, are appearing, you see, with R2. Okay? So this is important. I have to always make sure that I write the order in which the labels appear there in such a way that contiguous labels here are associated to the same variable in the integral. All right? Okay. So this is the integral appearing there. So alpha 2 prime, alpha 1 prime, v alpha 1, alpha 2. Okay? That's the matrix element that appears there. So, you see, more complicated. So 4 operators rather than 2. So I have now to destroy in all possible ways alpha 1 and alpha 2, and to recreate in all possible ways alpha 1 prime and alpha 2 prime, and the matrix element to put in front of these terms is this. Okay? It looks more complicated. It is more complicated than one-body operator, but it's still infinitely simpler than carrying all the sum over permutation and things like this. Okay? And unfortunately, I have no time to explain it to you today, but tomorrow I would like to show you a very interesting application of this. And this is the following. Suppose that you have 2 electrons only. And rather than having the 2 electrons in the ground state of helium, like last time we considered, you have really the 2 electrons to stay into 2 degenerate orbitals. For instance, remember that the p are really 3 states that are degenerate. Okay, so there is the p up and the p down. Suppose that I have 2 electrons only to put into 2 orbitals, not 3. Okay, so I will do a slightly simpler exercise. Suppose that I have 2 degenerate orbitals, okay, and I can choose where to put the electrons and with which spin I would like to put it. So in some sense, everything is forced. So you are not allowed to populate any other state in the Hilbert space but these two. A and B, call it. That could be A up or A down, B up or B down. Then the question is, which is the best state that Coulomb repulsion suggests? Okay? So in some sense, these states are degenerate as long as single particle energies. Okay? So for instance, the hydrogen-like levels are perfectly degenerate for A and B. Okay? So again, it's slightly simplified because 2 is not, I mean, there would be 3 for P, for instance. But let's simplify a little bit. So the single particle states are degenerate, but V, in first order perturbation theory, splits this degeneracy. So Coulomb interaction, we'll do next time, allows you to decide which are the best states that satisfy Coulomb interaction better. And we will discover that the best thing you can do is to put the 2 electrons both up, for instance, or both down, or in any case in a triplet combination. Okay? So when you have 2 electrons that occupy 2 orthogonal orbitals, the best you can do is to satisfy the maximum spin rule, okay? Rather than putting them in a singlet, like in the helium. Remember, helium was a singlet. You had only one object, and obviously, when you have one, you just put up and down. Pauli would forbid other things, okay? But if you have 2, now things change a lot. You do not prefer singlet, you prefer triplet. This means that typically atoms with degenerate orbitals tend to be magnetic, tend to be high spin. Okay? So a single carbon atom, for instance, in vacuum, would be magnetic because the 2 p electrons would like to form a triplet state rather than a singlet. Why? Coulomb interaction is better. We'll try to justify this next time as an application of some of this machinery. Okay? And we'll see how useful it is to have a second quantization language.